Hello. In this video, I'm going to be talking about how to predict how a reaction is going to occur. I could honestly save you guys 5 minutes and just summarize it in one word, but I'm going to go through it all. But the one word would be resonance. And well, what is resonance? Resonance is a way of describing bonding in molecules. It also describes the delocalization of electrons, and most importantly, it pretty much predicts how a reaction will most likely occur. I'm not going to say always because there's always an exception, but it is a very important term and something that will help you figure out how a reaction is going to go and why it's going to go in that specific way. So I'm going to go through an example where I'm going to use resonance to predict how a reaction is going to occur, where I'm going to take this starting material and I'm going to react it with NaBH4, and then I'm going to react it with CH3Br. So first things first, it's important every time you have like some sort of halogen or atom coming off of a carbon chain is just put in your electrons. Because if we remember when we did Lewis structures, we always drew in our electrons, and it's really important to keep count of your formal charges. That's why it's important to always show your electrons. So first things first, I see that there's a conjugated pi system, okay? What does this mean? It means that there's a double bond, then a single bond, and then a double bond. That is pi conjugation. Every time there's pi conjugation, I'm going to ask myself, can I draw a resonance form? Can that resonance form that I draw predict how my reaction is going to occur? The answer is most likely going to be yes. So first things first, let's draw a resonance structure. So draw our resonance arrows. Resonance arrows are two-headed arrows. And I'm going to take my electrons in my pi bonds and go 2 in, 2 out. So what do I get? Well, I have the 4 electrons that were originally on the oxygen. I gain 2 more electrons. I have a double bond here now, and I have a single bond there. What happens to that carbon? Well, that carbon becomes positive because it lost electrons. What happens to this oxygen? Well, if we calculate its formal charge, it becomes negative. So what does this tell me? Well, this tells me this is a form that the molecule is existing in. This is going to predict how my reaction might occur. And then I ask myself, well, is this resonance form stable? The answer is yes. And the answer to, well, why is it stable would be, well, let's talk about the periodic trends. And what periodic trend could I bring up? Well, electronegativity. Oxygen is a very electronegative atom. So we know that if we draw our partial charges in this original structure, I'm just going to erase these arrows, I would have a delta minus here and a delta positive here. What do we know about double bonds? We know double bonds are reactive. They're like sea otters. They're like snakes. They're going to jump out at any opportunity that they have to react. So this is really favorable to go 2 in, 2 out, because this oxygen does not mind gaining those extra electrons because it is electronegative. So this is how this molecule is going to react in this situation. So now I'm going to say, okay, well, now that I know that this is most likely negative, this likes to be positive, I can just hypothetically say, well, I'm going to toss in my NaBH4. Do we care about the Na? Absolutely not. So I'm just going to erase it. We care about the BH4. Do we even care about the BH4? Not really. All we care about is that BH4 is a source of H-. It is a powerful reducing agent. So I'm going to say I know BH4 is a source of H-. Why? Because boron usually will have 3 bonds, but right now it has 4 bonds. So what is that 4th bond going to do? Well, it likes to have 3 bonds, so it's most likely just going to eject that extra bond and be a source of whatever atom is that 4th bond. So right now, it's a source of H-. And now, well, we already did resonance, so what's next? Well, opposites attract. So now I can say, well, this is minus. You are a source of electrons. What does it mean to be a source of electrons? Well, you're a nucleophile. You are electron loving. You have those electrons. You never react things with positive. You need a minus charge, you need to have electrons such as a lone pair or a physical negative charge to be a nucleophile. You need to have the electrons to react with. So now I can say, okay, well, I'm going to take this negative charge and I'm going to hit this positive charge. So now, I'm going to draw an arrow in the forward direction. This is most likely in equilibrium, but that is an advanced organic chemistry concept that you can learn later in life, is when to put equilibrium arrows, when to not. Right now, you guys don't really need to worry about that. We're just trying to get concepts into you guys. So now I'm going to say, okay, well, I have this double bond, and now I just hit that positive charge with an H. So that means that that positive charge goes away. I just made a bond. The electron that carbon was missing is now occupied in a bond with the two electrons that came in and attacked with a 2-in type reaction. So now I can say, okay, well, what's left in the flask? Well, I have a CH3Br. So now this brings us back to our first concepts, is okay, well, delta plus, delta minus, establish partial charges. Why did I establish partial charges? Because opposites attract. So whenever I'm looking at how two things are going to react, one, I need to establish delta plus, delta minus. What that means is partial charges. And two, I can then say opposites attract. 3, then I can go 2 in, 2 out in most cases, unless one of them is already occupying or having a positive charge, meaning you don't need a 2 out. So this is a very important concept. Keep this in mind all the time. So now what do I know is that this is most likely going to get attacked. This bromine is electronegative, meaning that there is a dipole, showing that the electrons are moving towards and being pulled towards the bromine. So this bromine is going to end up accepting electrons from that bond. Now the question is, okay, well, is this minus just going to directly attack this CH3 and go 2 in, 2 out? That is a potential reaction that could occur. So now we can say, okay, well, one of the potential reactions that could occur is that, yes, that oxygen could directly go and it could directly attack that CH3, and then the bromine could go 2 out and go bromine minus. The other thing that could happen here is that I'm going to redraw the whole thing. We have this structure, we have an O minus, we have a double bond, we have a hydrogen, and we have a CH3. I'm going to draw it up here. We have a CH3 and a bromine. The other thing that could happen, well, I could go 2 in, 2 out, and attack from this carbon. And then the same thing happens, the bromine will still accept electrons. So then I will end up with a ketone, with an H, and a CH3 coming off of this carbon, and then I am going to be left with a Br minus. So hopefully this helps just with general knowledge of how to attack a reaction problem. I showed all things that could happen here because you guys aren't at a stage of knowing which one would be the best, in my opinion. Speak to your professor, though, to double check. Maybe he will have a better opinion on, what he wants you guys to think is more favorable or not at this level in the game in your university career. But hopefully this video helped you guys with predicting how resonance shows how a reaction will occur and just how to approach reactions in general. Thank you for watching. Hopefully this was helpful. Let me know if you liked this and what other things you guys want me to make quick videos on to help you guys do better on your next test and just generally succeed in this class. Thank you.